Hi, my name is Yu Zhang. This is my presentation for the design of my final project. The name of the project is numerical representation of mechanical interactions among flexible objects and particles. So first, brief introduction of the motivation. Currently, we have a much better computational power even from personal computer. So that gave us ability to do numerical simulations of more complex mechanical problems. And currently, we have already established some popular and widely used numerical methods, such as finite element method, discrete element method, and so on. And they all have their own advantage and disadvantage. For example, finite element method is relatively cheaper to be used and it's widely used. Most of the time, it could give accurate results, but it does have limitation. It has a continuum assumption, which means with finite element method, it's pretty hard to simulate the fracture of a material. On the other hand, discrete element method does not have this limitation. But in order to simulate the material, you need really large amount of particles that is expensive. So what I want to explore is if I can combine the different numerical methods to exploit their advantage and trying to avoid the disadvantage. And so I want to design a program to do that. In the meantime, since this is a computer science project, I want to utilize what I've been learning from computer science algorithm and the data structure to design the program to be as performant as possible. That involves extensive research on proper algorithms and how and on parallel computing, which gives me a high performance computing scheme. This is the objective of this project. So I would like to develop a numerical method that can resolve the coupling system of flexible object interacting with discrete particles. And so the one of the main tasks is to design the underlying data structure that will support the complexity and in the meantime the extensibility of the model, because this is going to be a prototype. This is going to be a simple model, but potentially people can extend the model to simulate a much more complex and much more interesting function. And I'm going to do some extensive research on the proper algorithm to be used for contact resolution, because this is one of the bottlenecks for the simulation and it's very expensive. And I also want to discuss the possibility of using parallel computing scheme to improve the performance of the program. This is so in the following, I want to talk about the main tasks of the project. So the first one is to establish the numerical description of the flexible object. In this one, I want to use finite element method called absolute nodal coordinate formulation. And here is a picture showing the geometrical definition, and the mathematical description of the forces in the system. So I'm going to use this to build the movement, to simulate the motion and the forces of the flexible object. Secondly, I need a numerical description of the particles, and there have already been discrete element method well established for me to borrow. So I'm going to borrow their contact model and the damping model. So this is demonstration of how this model should be established. And to move further, I need to be able to detect contactions between objects. That means I need to use the overlapping of objects to calculate the contact force and then push objects away. That gives the key that will give the key functionality of the model and will make the model reasonable and physically correct. So this is my current design thought process for the collision detection. I'm going to use some oriented bounding box concept to try to reduce the calculation for contact detection. In the meantime, after object has been contacted, I'm going to also borrow the contact model from the discrete element method to compute the contact force and push objects away from each other. And I also need some, the overall marching scheme will be like this. The first step is to use the current status of particle and flexible beam and marching to the next step with some high order marching scheme like Runge-Kutta fourth order that will give a better accuracy. And after the movement, I need to do contact detection to check if there are any overlapping, so I can generate correct contact force to push objects away from each other. After the contact force is generated, I can determine the acceleration and other status for the object. Then I can start over from step 1 for the next cycle. And doing this gives me the ability to marching from the initial condition to with respect to time. So I can do that. And looking into these steps, I could potentially have parallel scheme for step 1 and step 3. Step 2 is highly coupled, but there might be some reasonable deviation of the system that can help me to do to reduce the size for one calculation. So there are potentially parallel opportunity in step 2 as well. I'm going to discuss on that, explore the algorithms, and then do some optimization of my design model. And the next is the UML class diagram of the model. So this is I currently have established this model because this is a numerical method, so it's not going to have a lot of coupling of objects and the overall scheme is relatively simple. This one is small. Let me open the PDF to show a better picture. So the center of the system, the center of the program will be the system. And in the system, I have the object, physical object presenting. And in this case, it will be the beams, which are the flexible object. It can be potentially grass or maybe other stuff. And I also have particles. They are going to representing soil, sand, other particles. So it can be defined that way. The concrete definition of these two physical objects are here. For the beam, in order to do all of the proper calculation and definition, I need to know the some physical, mechanical, material properties such as Young's modulus, density, some geometrical properties as well, like length, thickness, width, area, inertia of the beam. And the following ones are for numerical calculation. I need to define the number of elements for the beam. I need to have a number of degree of freedom. Need to define the constraints of the beam and the rest, the three are the position, velocity, and the acceleration. So all of this are necessary for me to know the physical and geometrical configuration of the beam, and then I can march to the next step. I'll do contact detection. To support all of this functionality, I have this getter and setter functions. These are standard functions. I do not design any complex logic into the object, into the beam object, because I want to keep that into as a different engine such that the beam object will be relatively cleaner. Similarly, I have particle objects. So the fields are considerably smaller. I have the Young's modulus, I have density, and etc. And similar methods are designed here. And now for the main part of the method. These three object classes are going to help me define the forces and march into the next scheme. So the first one is force engine. The force engine have a gravity. This is gravitational acceleration. And then I have the following methods to help me calculate the gravitational force, elastic force, constraint force, constraint load, and distributed load and contact force. So that will be implemented to help me do all of the force calculation. There is also a utility class I designed to get some of the basic mathematical values of the model, like Gauss points, shift function of the model, and this is doing the cross product to help me do cross product. And this is to calculate the mass matrix of the beam, etc. So this ones will be helpful for me to do other calculations, integration or other stuff. And the next one is time marching. It only has the range quota because that's the only one I need. But potentially I can extend to more methods because different methods could have a different performance. Range quota is very popular, but I might extend to predictor adapter method to help improve the performance of the model. So this is the overall scheme of my model. It has a relatively simple structure. The main design will be for the mathematical calculations, and there might be some new some more consideration on how to make sure I do not waste a lot of memory and performance on the model. But that's for future steps. Right now, this is the overall structure. So that's my presentation for the project. Thank you very much.